Welcome to Wireless Fundamentals, Session 12, Introduction to Security. This section introduces basic WLAN security concepts. Ethernet networks have a certain amount of inherent security. The corporation owns their own Ethernet infrastructure and so can strictly control configuration and physical security. The Internet, by comparison, is relatively unsecured. There are many entry and exit points which are not under our control. This is why we use a suite of security protocols when we need to secure communications over this unsecured medium. We'll use protocols like IPsec or SSL tunnels. Like the Internet, wireless is not inherently secure. Radio waves emanate in all directions, often outside the boundaries of our office space and into public areas. Also like the Internet, we can use a collection or suite of protocols to secure our wireless communications. Let's review the endpoint connectivity process and where these security suites are implemented. Do you recall our earlier discussion in Session 4 about how endpoints connect to an SSID? The process begins with a probe request. APs receive the request and respond with a probe reply. The endpoint chooses the AP with the best signal strength for connectivity. Next is the authentication request. With the open authentication method that modern WLANs use, the AP sends an affirmative authentication response. This is actually more of a pre-association handshake than an actual authentication mechanism. Next, the endpoint sends an association request. The AP receives this request, creates an association ID to track the client info, and responds with an association response. The client is now connected. The endpoint then acquires an IP address via DHCP. However, we need to provide real security for corporate connections with supplemental authentication. This is where the collection or suite of security protocols happen. They ensure that only authorized users are allowed to access the network and protect wireless communications from eavesdropping and tampering. There are 3 protocol suites available for us to choose from. They are called Wired Equivalent Privacy, or WEP, Wi-Fi Protected Access, or WPA, and 802.11i, or WPA v2. Let's explore these security suites in more detail. Wireless security protocol suites, as well as Internet security suites like IPsec, all provide a very similar set of services. Encryption is used to prevent others from viewing our data. We need to keep our communications private. The anti-replay service prevents others from modifying our data without detection. Authentication ensures that we only share data with appropriate parties. In order to access the WLAN, you must provide valid credentials. We will discuss various authentication mechanisms. For 2 endpoints to successfully encrypt and decrypt data and add hash values and then check their validity, each site requires compatible key information. Once a user successfully authenticates, valid keys must be distributed to the AP and the endpoint. These keys are used for encryption and anti-replay services. Algorithms like TripleDES, RC4, and AES are all encryption algorithms. They convert legible data into cipher data. Alice's message, "Please pay Vivek $1,000, is fed into an encryption algorithm. The algorithm converts the message into ciphertext using private encryption key information. Bob has a compatible key, and so when he receives this message, his endpoint can successfully decrypt the message. Any evil ogre who may see the message will not be able to read its contents. They do not have this private key information. Algorithms like CBC-MAC and MIC or MIC are hashing algorithms. They perform a mathematical calculation on the unique contents of a frame. This is similar to how Ethernet performs a unique cyclic redundancy check, or CRC, on an Ethernet frame and places the result in a special CRC frame field. The difference is that a hashing algorithm uses unique key information to encrypt the result. Alice's message, "Please pay Vivek $1,000, is transmitted with this special hash value, or fingerprint, if you will. Unfortunately, the evil human intercepted this message and changed the value from $1,000 to $100. He then forwards the message on to the intended recipient. This might be a bad day for Vivek. Fortunately, when Bob's endpoint receives the message, it is run through the same hashing algorithm using a compatible key. His endpoint detects that the hash value does not match the data pattern and discards the frame. As you can see, encryption and hashing algorithms offer powerful mechanisms to protect our data, and both rely on each endpoint having compatible key information. Let's talk about how this key information gets distributed. WLAN authentication mechanisms serve two primary objectives. The first one is obvious. We know that authentication is the process of checking credentials to permit or deny access. You will soon learn about the two methods of controlling WLAN access: static pre-shared keys and dynamic 802.1x authentication. Regardless of which method you use to grant access, the second objective is the same: generate and securely distribute key information to the WLAN client and its associated AP. These keys can then be used to encrypt and add a hash value to each transmitted frame, and then to decrypt and check the hash value of each frame received. Now that you have a general understanding of the components of a security protocol suite, let's compare the individual components of actual, real-world protocols that you may need to configure. Recall that a security protocol suite performs encryption, anti-replay, authentication, and key management. Consider a protocol suite like IPsec. True, this is not related to wireless technology, but it shows that regardless of the medium, the required services are the same. IPsec can use DES, triple DES, or AES encryption, and these are listed in order of computational security. DES and triple DES have become dated and are not commonly used. The best encryption algorithm commonly available to the general public is the Advanced Encryption Standard, or AES. For anti-replay, you can choose between Message Digest 5 or a Secure Hashing Algorithm, or SHA. Authentication can happen by using pre-shared keys or a more robust mechanism using a Central Authority, or CA service. After successful authentication, keys are distributed to the two endpoints using the Diffie-Hellman algorithm, or DH. The oldest WLAN security mechanism is called Wired Equivalent Privacy, or WEP. WEP. The way this protocol was implemented creates serious security weaknesses. It is relatively easy to hack a network using WEP. Also, there was no attempt at preventing man-in-the-middle attacks. WEP uses a simple CRC32, like Ethernet. Since this value is not encrypted, anyone can intercept and modify a frame, recompute the new CRC value, and then replay it towards a recipient without detection. For authentication, a simple key is used. Everyone connected to the same SSID uses the same key for authentication, and the same keys are generated for everyone to use for encryption. Unless you have some very old client devices that only support WEP, there is no reason to use this vulnerable protocol today. Several years ago, the IEEE 802.11i committee began work on a very robust suite of protocols. However, this work would take a couple of years to complete. An interim solution was devised to provide huge improvements in security until the new protocol suite was ready. This interim suite of protocols is called Wi-Fi Protected Access, or WPA. WPA still uses the same RC4 encryption algorithm used by WEP. However, it was vastly improved by using more robust key mechanisms. The Temporal Key Integrity Protocol, or TKIP, is a kind of protective wrapper around the RC4 encryption mechanism. This protocol mixes unique client information into the key stream to generate a far more secure encryption result. WPA also uses an actual hashing algorithm called Message Integrity Check, or MIC. You can choose to use a simple pre-shared key for authentication, or a more robust username-password mechanism based on 802.1x and an Extensible Authentication Protocol, or EAP. Like WEP, everyone uses the same PSK for authentication. However, each user gets its own unique set of keys for encryption and hashing. This is far more robust than WEP. WPA is a huge improvement over WEP. However, the IEEE 802.11i suite of protocols has been completed for a few years now. Often referred to as WPA v2, this protocol suite uses very strong AES encryption, and hashing is also based on AES. This is the most robust security currently available in the industry, and all modern devices now support it. For every day that passes, there is less of a reason to use anything other than the WPA v2 protocol suite. For authentication, you can use simple PSKs or a more robust EAP-based mechanism. Before we move on to compare these two authentication mechanisms, let's take a moment to consider the protocol suites you see here. In a real-world diagnostic setting, it is less important to understand the arcane details of how each of these protocols work. If the protocol doesn't work, then there is a bug in our operating system. That is the problem of a software engineer. We are network engineers. We need compatible configurations on each device. If you were doing packet captures and saw indication that an endpoint was using TKIP or MIC, you'd know WPA was configured. Looking at the AC, you may see that it expects WPA v2. See, you need to know that WPA v1 uses RC4 with TKIP for encryption and MIC for hashing. You need to know that WPA v2 uses AES for encryption and hashing. Enough about encryption and hashing then. Let's look at authentication mechanisms. The big advantage of using PSKs is simplicity. You simply configure an AC's SSID with an ASCII or hexadecimal key string value. You then configure each endpoint with the exact same value. Done! The endpoint and the AP do the typical probe request response, open authentication and response, and the association request and response. However, the response includes a challenge for PSK authentication. The endpoint uses its PSK to create a hash value and response. The AP uses its PSK to validate the response and, if successful, sends a success message. As typical, the simplicity of PSKs mean that they are not scalable. You might need to manually configure PSKs on 1,000 laptops. If an employee leaves the company, PSKs may need to then be changed on all the endpoints and on all of the WLAN systems. Also, it is more difficult to track individual user activity. You might be able to identify a MAC address and then assume that the owner of that MAC address was the one using the device. There's still a high level of plausible deniability. In other words, a user can say, "It wasn't me." Still, Many small and medium-sized organizations find PSKs to be a viable solution. Let's take a look at configuring PSKs. To configure an SSID for WPA2 PSK, Virtual Interface WLAN ESS3 is created as a hybrid port. PVID11 is configured. This is a basic local forwarding configuration. Now we configure the security portion with 3 port security commands. One sets the mode to PSK as opposed to user login. Another sets the key type to 11 key. There is no other option, but this is required for PSK configuration. The final command configures the actual PSK or pre-shared key value. In this scenario, it is secret 123. Next, a WLAN service template is defined as a crypto SSID, and the SSID is defined as corp. The AP is also made responsible for performing authentication locally, and AP beacons will not include this SSID. The virtual interface is bound to the service template. Now for the security portion of the configuration. The cipher suite is set to CCMP, which means we intend to use WPA v2's AES encryption. The word TKIP could have been used if we would have wanted to use WPA v1. The security information element, or IE, is set to RSN, which again selects WPA v2. The keyword WPA could have been used to select WPA v1. The authentication mode is set to local, and the service template is enabled. The service template is bound to an AP with the command service template 3, and a configuration file is specified. As we discussed in a previous session, this ensures that the AP also supports VLAN 11. As a review, the text file is shown here. This file can be created on any machine that has an FTP server process running. Then you can use the FTP client feature of the Unified AC to copy the file from the server and onto the AC file system. The APs are power cycled, and they will then load this file into their local configuration. PSKs are simple, but for a scalable solution, you need to use 802.1x with an Extensible Authentication Protocol, or EAP. Several components are involved. The supplicant is simply the software on a client endpoint that supports 802.1x authentication. Nearly all modern devices include this supplicant: PCs, iPads, Android devices, and more. The authenticator is the device that controls endpoint access. For local authentication, it is the AP. For central authentication, it is the AC. For wired endpoint access, the authenticator would be the directly connected switch. 802.1x EAP messages are passed between the supplicant and the authenticator, including user credentials. The authentication server is a Radius server. This can be in the form of the Microsoft Policy Service running on a Windows Server, HP IMC Management Platform with the UAM module, or any number of other third-party Radius products. The Radius protocol is used to communicate between the authenticator and the authentication server. The supplicant supplies credentials to the AP with 802.1x. The AP harvests these credentials and forwards them to the Radius server in a Radius message. The Radius server checks these credentials against a user credential data store. This could be a local store on the Radius server itself. Or the Radius server can be integrated with a Microsoft Active Directory system or some other LDAP database. If this is the case, the Radius server sends a request to the external data store. Please validate username Gerline, password secret123. The Active Directory responds, yes, that user is valid. The Radius server creates a Radius message and sends it back to the authenticator. User is valid. The authenticator informs the endpoint and allows network access. In most cases, a certificate authority or CA service will also be involved. This service is responsible for generating, tracking, storing, and validating certificates. These certificates can then be used to prove authenticity. There are several different types or flavors of EAP. EAP TLS is considered the most secure, but requires both server and client certificates. The initial setup and complexity involved in deploying and maintaining CA servers can be significant. However, many organizations are already using CA services for other purposes. If this is the case, then this is not an issue. Once the CA service is up and running, certificates must be generated and distributed to all servers and every single client device. This distribution used to be very tedious and labor-intensive. However, with modern policy servers and BYOD solutions, this can now be largely automated. PEAP is also very secure, but with the advantage of only requiring server-side certificates. No need to distribute client-side certificates. However, you still must deploy and maintain a CA service. And since client certificate distribution has become easier in recent years, this is less of a distinct advantage than it was in the past. PEAP has two common variants. One is PEAP Generic Token Card, or PEAP GTC, and the other is PEAP MSCHAP v2. EAP TLS and PEAP MSCHAP v2 are by far the most common EAP flavors in use today. There are others, but they are far less common. This includes LEAP, a Cisco proprietary type that is very easy to configure since there's no CA. However, usernames are sent over the air in the clear, making it vulnerable to brute force password hacks. EAP Fast is another Cisco proprietary method. It is very easy to configure since no CA is required. EAP TTLS is very similar to PEAP, but it is not in widespread use. This concludes HP's WLAN Fundamentals series. Thank you.